All right, so we're talking about PV work. You're typically talking about P delta V.
Mm-hmm.
When you do work on the system, this results in a gain of heat. Q is greater than 0, which means delta H is greater than 0, which means the process is endothermic.
Okay.
In an endothermic process, the delta S of the surroundings is less than 0. Now, when you do work on the surroundings, of course, that's a release of heat. The Q is less than 0. Delta H is less than 0, which means the delta S of surroundings is greater than 0, and we call that exothermic.
So if I say that delta S is greater than 0, then that means
Well, you
it's
got to be
going
careful
toward
what
more
you
disorder?
got to be careful about the difference between delta S of surroundings and delta S of the system. When we normally talk about entropy, we're talking about the delta S of the system.
Okay.
Now, the delta S of the system plus the delta S of the surroundings must be greater than 0 if it's going to be spontaneous. We, rather than looking at the delta S of surroundings, we look at the delta H of the system. And so long as delta H of the system minus T delta S of the system is less than 0, which means delta G is less than 0. Of course, that's spontaneous. But the root of delta H of the system is actually, it's a measure of the delta S of the surroundings. So when I release heat, energy helps to increase the disorder that is present in the surroundings. And in fact, energy has a much larger part in the entropy of the surroundings than does the number of molecules that I create. So that energy can be spread out or distributed in lots and lots of different ways.
Okay.
So this is the way that you're probably used to seeing it, but this is the ultimate measure, this one right here. So now that we've done that, let's look at some questions. So we're looking at passage 2 in the Berkeley Review. Passage 2. We're in TBR G-Chem 2, Section 3. And if you have the online PDF, we're talking about page 171. So notice that we're first given a form of Hess's law where we depend on bond enthalpies, and we have a table. We have a second table with multiple bonds. And let's go right to the question. So question 8 asks, which is the weakest bond in diethyl peroxide? You know, I believe it's going to be C, but let's look at the data. So, of course, the weakest bond will have the least amount of energy required to homolytically break it. So let's talk about that for a second. So if I have a bond XY, homolytic bond dissociation is how bond energies are typically measured. This has a big implication in organic chemistry as well. So each electron in the bond splits itself equally, and one goes to X and one goes to Y, so you get two radicals. And these are neutrally charged. So, greater bond dissociation energy equals stronger bond. So all we're going to do is look at the mathematical data. Now we've already seen that an oxygen-oxygen single bond is 146. We also need to look at a carbon-oxygen, a carbon-hydrogen, and a carbon-hydrogen. And so we're going to need to scroll up to table 1. And so a carbon-hydrogen is 413. A carbon-oxygen is 358. And a carbon-carbon is 347. Clearly the weakest bond is the oxygen-oxygen single bond. That shouldn't surprise us. That's how peroxide decomposes. So as we go back to look at our answer choices, which bond is the weakest? It's clearly going to be answer choice C, the oxygen-oxygen single bond. Okay, what is the bond energy of the second pi bond in nitrogen gas? All we really need to do is look at nitrogen-nitrogen double bond versus nitrogen-nitrogen triple bond. Because technically, the only difference is an extra pi bond. Nitrogen-nitrogen double bond is 418, while a nitrogen-nitrogen triple bond is 941. I subtract the two, that's 523. Pretty big difference. That's answer choice D. So number 9 should be D. All right, number 10. Okay. Why does an sp2 carbon sp3 carbon bond have a higher bond energy than sp3 sp3? My answer to that is going to be resonance. Even before I look at the answer choices. So really what we're asking is, why is this carbon-carbon bond longer than this one, even though carbon 2 and 3 is a single bond? And what I would suggest is, I can draw a nice resonance structure here so that this has partial double bond character. Of course, this is going to be negatively charged and this is going to be positively charged. A little carried away there. There's no partial double bond character here. So that's what I suspect before I even look at the answers. Let's start with what I don't like. An orbital is not electronegative. That's silly. I'd get rid of C and D right away. So I would say A is really good. sp2 orbital, if it is shorter, that means that there's more orbital overlap, which means the bond is shorter, which means the bond is stronger. A is the best answer. I'm not in love with the way they state this, by the way. We really don't talk about an orbital being short or long. But what they're implying is the orbital overlap is stronger, and that's because there's more volume, which brings the nuclei closer together, which decreases the length of the bond. So it's all in the way that it's worded. There's less of a risk with A than there is for B or C or D. Remember, your job is to find the best answer. The answer is the least full of shit. A is the least full of shit in this case. Okay, so let's look at 11, and all we really need to do now is some pure mathematics. Okay, so if I break an H bond and an F bond, and I make 2 HF bonds. We want to compare the combined energy of these two to the combined energy of these two. And if the products are stronger bonds than the reactants, it's exothermic. If the reactants are stronger than the products, then it's endothermic. And the difference between the two will be able to give us the difference between highly and slightly. I don't like the words highly and slightly, but we'll just go ahead and beat them at their own game. So HH bond is 432, and an FF bond is 154. So if we combine those, we have 586. HF 565 times 2. That's going to be 1130. Way stronger. So, first of all, we know it's exothermic, so we can get rid of A and B, and it's pretty significantly more exothermic, so I would get rid of C as well, and I would choose D for number 11. These are good, basic bond enthalpy questions that I could see being on your test. Probably not as many easy ones as this one has, but these are all decent Mcat questions. How can the bond energy trend of the sulfur halide bond be explained? So the first thing you have to do is to identify the trend of the sulfur halide bond. So we could do SF, SCl, SBr, and SI. SF doesn't look like it's measured. SCl is 258. SBr is 218. That's going down. But then for SI, it's 266. So that's an interesting dip. Okay, so as the halide gets larger, the bond gets stronger. No, not necessarily. Because it's not, so bromine is larger than chlorine, but the bond strength's going down. So we've got to have something that is rather complicated. A is too simple. B is also too simple. Because here, it's going down even though bromine's more electronegative than iodine, so that doesn't work. As the electron affinity of the halide increases, again, you got a dip. The strength of bond depends on both size and polarizability of the halide. That's the best answer because this is at least introducing the fact that it's more complicated than a simple rationale. That's what you want to do.
Okay.
What is the approximate bond energy of a BRF bond? This is what I would do. Quite simply, you got to look at a pattern. Shift this.
Sorry.
So, what do we know from the data? We know we're trying to find a BRF bond. BRF. Do we have a BRCL bond? Do we have an FCL bond? Do we have an FI bond? Do I have an ICL bond? So, first of all, we have, here we go. We have an FCL bond of 253. So this is 253. Also, we have a BRCL bond of 218. Do we have an FI bond? I do not see one. We have an IBR bond of 175. Do we have an ICL bond? Yes, 208. There is no IF bond. So a BRF bond, BRF. We do have BRCL. Do we have BRI? We do. We have BRI. And BRI looked to be 175. 175. BRCL is 218. We could also look at this from FCL, FBR. FCL is 253. Now I don't have an FBR and I don't have an FI, so that's a problem. So I think greater than 218 makes sense to me. And it looks like the smaller these get, the stronger the bond gets. I think it's got to be less than 253. So the BRF bond must be greater than 218, but must be less than 253. Now that we've got that bookended, let's look at our answers. Got to be B. Mm-hmm. It's the only thing that makes sense. So for 13, that will be B. Classic chemistry question: why is the FF bond weaker than the CL-CL bond? Fluorine is so small, the nuclei get so close together that the protons in the individual atoms repel each other, which is going to be C. That is a classic chemical question.
I did.
This one. All right, so we're going to look at the Born-Haber cycle. First question: if sodium metal was used instead of lithium metal, we can look at a couple of basic trends here. First trend we can look at is ionization energy. Ionization energy is defined as the amount of energy. So by definition, this is an endothermic process. Needed to convert an element X into a cation by removing an electron. Now, lithium versus sodium. Highest energy electron is a 2s1 versus a 3s1. Sodium is larger, which means its valence electron is farther from the nucleus, and so sodium has a smaller first ionization energy. So let's look at our statements. Ionization energy would increase. We know that's absolutely false. So 2 cannot be part of answer. And so let's look at what our answer choices are at this point for A, B, C, and D. 1 only, 2 only, 1 and 2, 1 and 3. 1, 2, 1 and 2, 1 and 3. So we know right off jump that these cannot be part of the answer. So all I need to do, I don't need to look at statement 1. It'd be foolish to look at statement 1 because statement 1's part of both of the remaining answers. Only look at statement 3. The lattice energy would increase. Actually, the lattice energy would decrease. And this is why. Sodium is a larger ion than is lithium. That means if I have the same cation, no matter what it is, let's just say it's this. Think of 2 dancing partners. Here's a principle of chemistry here that applies to life. Listen carefully. It's 2 fatties cannot slow dance. Ever. Only so close together you can get. 2 skinnies, babies are made. They can get close and do a lot of damage, but not 2 fatties. So this means that the lattice energy would decrease for sodium. If we look at the answer choice, it's the opposite. So it can't be D either, which means it must be A. And we don't have to evaluate statement 1. We know it's got to be the best answer. All right, number 16. Why is only half of the dissociation energy used in step 3? Probably because you want an F atom. Yeah. If you have half of a F2 molecule, you have an F atom.
Okay.
I would answer D. It's the most practical reason. You can't partially break a bond. That's silly. B. That's silly.
Okay.
C. It's not broken heterolytically. It's broken homolytically. D is the best answer.
Okay.
All right, 17. All right, let me show you the foolproof way of always getting 17 right. So we're looking at NaCl, LiF, and MgO. There are two factors that affect lattice energy. One is the charge, and two is the size. In other words, charge distribution is what ultimately determines the lattice energies. Charge is more important than size. So if you look at the charges of your ions, and this is where ions and charges are critically important, MgO is going to be the largest because its charges are +2 and -2. So what I tell anyone that I tutor is just to take the product of the two charges and then take the absolute value. This would be 1, this would be 1, this would be 4. MgO has the greatest lattice energy. So look at our answer choices. C and D cannot be correct. Get rid of them.
Right.
Now, let's go back up to our mantra. Two fatties can't slow dance. All right? That means sodium is bigger than lithium, chlorine is bigger than fluorine. That means these are larger. This will have the smallest lattice energy. These can get closer together. So NaCl should be listed last, which makes A the best choice. Two considerations, the charge and the size. Okay, if calcium metal is used instead of lithium metal, how can the value in step 2 be determined? You've got to have the ionization energy for both of those, and so you should take the sum of the first and the second, because that's how much energy it takes to make the cation.
Okay.
It's not Ca+. Only the value for the second ionization, no, because it occurs as a metal in nature. So B doesn't make sense. Averaging 1 and 2 doesn't make sense. It's how much energy is needed to make the appropriate metal cation. So D is the best answer.
Okay.
Electron affinity. Okay, another nice periodic trend to know. So electron affinity refers to the amount of energy that is released when an element takes on an electron to become an anion. So this is intrinsically exothermic. There are a few exceptions where you can have endothermic. But for the most part, it's exothermic, because adding an electron to something that has a nucleus, you're making a bond, not breaking the bond. D, the energy associated with the gain of an electron. Which change results in less energy being released. Using a cation that can easily lose a second electron. You would use more energy there. Using a halogen atom with a greater electron affinity than fluorine, no such atom exists.
Right.
Using a halogen that forms a stronger bond as a diatomic molecule than fluorine, that would result in less, because it would take more energy to break it. So I would answer B with that one.
Okay.
21. What changes would reduce the lattice energy? Certainly 1 would, right? Two fatties can't slow down, so 1 is part of the answer. Of course, we should have never looked at it, right? Because 1 is in every answer choice.
Right.
Substituting an anion of less charge for the anion. 2 is also true. So now I can get rid of A, I can get rid of C. Reducing the cation charge, the anion charge, and the distance between ions by half. Coulomb's law is what governs this process. So let's just imagine for a moment that we have a charge of +4 and -2 and a distance of, let's say 16. So we're going to reduce all of these by a factor of 2. Coulomb's law says the force is equal to the constant K times the product of the charges divided by R squared. So this means 4 times 2, I'm going to ignore the negative sign, over 16 squared. So this is 8 over 16 times 16, which is 1 over 32. Let's do the same thing over here. We got K times 2 times 1 over 8 squared. That's 2 over 64, which reduces to 1 over 32. They're exactly the same. So that doesn't result in a lattice energy that's reduced. So the best answer should be B. And I think plugging in numbers is the best way of handling that.